Morning everyone, happy Ring Friday. I have a video for you today on cell potential, electrical work, and free energy. So lots of stuff in this video to kind of connect together our last unit and this unit on electrochemistry. All right, in our last unit, we saw that a reaction will go on its own, not necessarily fast, but it will go if it is thermodynamically favorable. So if I'm looking at a redox reaction, I can decide if a redox reaction is thermodynamically favorable by looking at the E cell value that we calculate when we take the reduction value at the cathode minus the reduction value at the anode. If your overall E cell value is positive, the reaction is thermodynamically favorable. That means we are getting a voltage on the wire, the electrons are moving on their own, it's a thermodynamically favorable reaction. If your E cell is negative, then it is a not thermodynamically favorable reaction. The electrons will not be transferred on their own the way the reaction is written. So there's very clearly a relationship between delta G, Gibbs free energy, and our E cell value, because we know when delta G is negative, the reaction is thermodynamically favorable. We now know that E is positive. If delta G is positive, that means the voltage, that E value, must be negative. So I call this the giraffe equation. That is not legit or scientific, but for some reason, it just reminds me of the word giraffe, and I don't know, you get like a tall tree and the giraffe, I don't know. Okay, work with me here. I know the word giraffe has no N in it, but again, yeah, you do weird stuff to remember things. So I call this the giraffe equation. And so the N in the giraffe equation is the number of moles of electrons that are transferred in the redox reaction. It's always a positive number, but we put the negative sign in front of it. So the negative number of electrons that we are transferring in the reaction when it's balanced. F is Faraday's constant, which is 96,485 coulombs per mole of electrons transferred. So that unit is coulombs per mole, but I'm referring to the moles of electrons. And then E is your E cell value. Okay, E cell can be measured in volts, but 1 volt is the same as 1 joule per coulomb, and so that's how we're able to get our joule value for delta G. If you look at your units canceling, coulombs will cancel from the E cell right here, and from Faraday's, moles of electrons cancels from the N, and then the bottom of this Faraday constant, and so we're left with joules for our unit for delta G. So, I'm here. Gibbs free energy is the energy available to do work. That's essentially how we are using the free energy when we solve for it. So the maximum amount of work that can be done by a reaction is the same as delta G. Under standard conditions, delta G is right here, and we know that delta G is equal to the negative NFE. All right, this problem says calculate the E cell for the reaction. I have a redox reaction here. I've looked up the delta G of formation values for you. That's in kilojoules per mole. So I have those values. Don't forget, we're gonna have to turn it into joules before we plug into the giraffe equation. But this is kind of involved because in order to use the giraffe equation, we need to solve for delta G, and we know we can do the products minus the reactants. I have those values for you, so that's good. That's a review of last unit. But we also need Faraday's constant, which is given to us on our equation sheet, and we also need the number of moles transferred in this redox reaction. So we are going to have to assign oxidation numbers, figure out what's oxidized and what's reduced, split it into its half reactions so that we can get to the point where we know how many electrons will be canceled out in our balanced redox equation, because moles of electrons needs to be plugged in. So I want you to pause the video and set a timer for 4 minutes. You're going to do products minus reactants. You're going to start to balance the redox reaction and up until the point where you figure out how many moles of electrons will be transferred, and then you're going to plug into the giraffe equation and solve for your delta G, solve for your E value, and that's going to be in joules per coulomb, which is the same as volts. So pause the video, set a timer for 4 minutes. I'll put the answer up in 3, 2, 1. All right, here we go. I started by solving for my delta G, products minus reactants. So there's 1 CO2, 2 waters, those are all added together, minus 1 of the CH3OH, plus 3/2 of oxygen, which at its standard state is 0 for delta G and delta H. So I'm going to take my products total minus my reactants minus a negative. I'm adding that. I get negative 702 kilojoules. And so that will, when we multiply that by 1,000, that's negative 702,000 joules. Now I assign my oxidation numbers here, and I see that my carbon went from a -2 to a +4, which means it's losing electrons, so it is oxidized. So I start to balance. I notice that this side has 4 hydrogens. This side has 2 oxygens, this side has 1, so I add 1 water. Now on this side, we have 2 hydrogens plus these 4 hydrogens, right? That's a lot of hydrogens over here. So we have 6 hydrogens total. We add 6 H pluses. And then if you look, this side is neutral in charge. This side has 6 positives, so we add 6 electrons. My oxygen, because it's standard state, starts at an oxidation number of 0, and then it goes to -2 in 2 different positions. Either way, it's gaining electrons. So I have my O2 to my H2O. So on this side, I have 2 oxygen, so I put a 2 in front of the water. That's 4 hydrogen, so 4 H pluses. On this side, I have a +4, and this side I have 0, so I have 4 electrons. I'm going to multiply this reaction by 3 halves, which makes sense, right, why we saw the 3 halves in the balanced equation. That way I can see we're going to have 6 electrons transferred. So I now have my delta G value, negative times 6 moles of electrons, my Faraday's constant in coulombs per mole of electrons, and we're solving for the E cell. So I do a little algebra. I get my E cell as 1.21 joules per coulomb, and that translates to 1.21 volts. Notice my delta G was negative, which indicates that this is a thermodynamically favorable reaction, and my voltage is positive, also indicating a thermodynamically favorable reaction. So your delta G and your E cell are related. All right, this is from your problem set number 3, question 65, so let's do it together. So I have a galvanic cell, and these are the 2 half reactions it's based on. Notice they're both written as reductions. So I looked up the E cell value, 0.80 volts and 1.78 volts. And then I want to know if the E cell is going to be bigger or smaller than the standard cell. So let's talk about the standard cell before we look at what they're changing. A standard cell means we have 1 molar of anything aqueous. It's at 25 degrees Celsius, and if there's any gases, those gases are at 1 atmosphere pressure. So like if we had like H2, hydrogen gas, oxygen gas, anything like that. So I'm looking at these values, and I see that my bigger reduction potential, the more positive one, that means it's going to be reduced, and that's our cathode. And this one must be oxidized, which is our anode. So if we wanted to write a full balanced equation, I would have to flip this top reaction because it's the oxidation, because they're both written as reductions, and I see 2 electrons and 1 electron, so we're going to have to multiply this by 2. So let me write the full normal balanced equation with the electrons all canceled out. It would be H2O2 plus 2H plus 2Ag solid makes 2H2O plus 2Ag plus aqueous. So there's my normal balanced equation. I can also calculate the E cell under standard conditions because I know it's the standard reduction potential at the cathode minus the standard reduction potential at the anode. And so when I do my standard under normal conditions cell, I'm going to take 1.78 minus, and so my standard cell, when they're all 1 molar, is 0.98 volts. So we have a balanced equation. We have our voltage under standard circumstances. Now let's look. I actually want that reaction again, so let's do this. H2O2 plus 2H plus 2Ag makes 2H2O plus 2Ag plus. So what they're doing here is we still have our Ag plus at the same 1 molar, that's standard, but they're increasing the concentration of the H2O2 and the H plus. So these are larger in concentration. I want you to think of Le Chatelier principle back from when we learned equilibrium. So if I increase the concentration of reactants in order to reestablish equilibrium, the reaction is going to shift towards the products. So I'm increasing from standard conditions the reactants, so we're going to shift to the right. And by shifting to the right, that means more electrons are going to be transferred in this redox reaction, right? If the reaction keeps proceeding, that means more of these electrons that we canceled out will be transferred, which means this new E cell value will be larger than the standard value because there's going to be a greater voltage if more electrons are transferred on the wire. Why don't you try this one? Look at the balanced equation, see what they are changing, and decide if your E cell value is bigger or smaller than your standard E cell value. Pause the video and try. All right, so hopefully you noticed that they were lowering a reactant, smaller concentration, and increasing a product. And so that both of those indicate we're going to shift to the left, which means your new E cell value is going to be less than your standard E cell value, because if we shift toward the reactants, that means less electrons are being transferred on the wire. So our voltage from this new E cell will be lower. Okay, I want to circle back to our Ratlink equation from last unit. So if you remember, we have this delta G equals negative R, which is one of our gas constants with joules in it, the temperature times the natural log of your equilibrium constant. And so we use this to find delta G under equilibrium conditions. So we've established equilibrium and we're under standard conditions. What is our delta G? What if, though, we are not at equilibrium? We could use this variation. Basically, here's our standard delta G, and we're adding an adjusted value, the gas constant, the temperature in Kelvin, and then the the natural log of Q, which is where we plug in the concentrations of our products over reactants not at equilibrium. So basically, we're taking our standard value and either adding or subtracting, depending if this result is positive, the adjustment, so to speak, when we are not at K, we are at Q, to get this other delta G. So we saw this last unit. There is a relationship, though, that we can find that's similar to these delta G kind of variations, and it's called the Nernst equation, and it gives us the relationship between the cell potential and the concentration of the cell components if we're not at 1 molar for everything, which is a lot of the time. So we can take our standard E voltage, that essentially here's what the voltage would be if everything were 1 molar. We can subtract from it 0.0591 over the number of moles that are being transferred in the balanced redox equation times the log of Q, and Q is the concentration of the products divided by the reactant. So this is your reactant quotient from our equilibrium unit. And so that will give us the new E value. So again, a lot of times we will start a galvanic cell with everything at 1 molar, but as it runs, remember, we're adding more ions, usually on the anode side, and we're removing ions on the cathode side. So usually our concentrations do not stay at 1 molar for very long. We're using some up and making some, depending on what cell you're looking at. So that will change our molarity, so it will change what we get for Q, so we can plug into this equation to solve for the new voltage. So again, here's a variation of the Nernst. So we have our Ratlink. This is used to find delta G under equilibrium and standard conditions. If we want to just find E when we're at equilibrium conditions, right, and we're standard, which is really 1, we will use this E equals 0.0591 over the number of moles times the log of K. And then here's the variations. The variation on Ratlink when we're not at equilibrium because we're solving for Q. And here's the Nernst equation that we will use if we're not at equilibrium. Essentially, we have adjusted the concentrations in those half cells, so we need to find the new voltage. So the reality for us is we're going to use this guy if we're at standard conditions. We're going to use this guy if we're not at standard conditions. All right, this is objective number 3, number 72. Consider the cell described below. So we have the anode electrode is aluminum, solid aluminum, and it's dissolved in 1 molar, or we have a solution of 1 molar Al3+. And then we have our double line for the cell notation. So now we're going over to the cathode. The solution is Pb2 plus ions at 1 molar. A single line tells me that the electrode is solid Pb. So here I kind of drew out a picture, and we have our salt bridge. It says calculate the cell potential after the reaction has operated long enough for the aluminum to have changed by 0.6 molarity. And it says that we are at standard temperature. So let's take a look at this one together. Okay, so the first thing is I have to write both of these half reactions as reductions. So to figure out the reduction, we know we are gaining electrons, right? Gain electrons reduction. So I take my Al3 plus 3 electrons to make neutral. I knew we had to get all the way to the neutral because of the electrode. Same with the Pb. Pb2 plus 2 electrons makes solid Pb. I look up the reduction potentials, and I see that the reduction of the Pb, right, is clearly the larger value or the more positive value. So reduction cathode is the Pb, which means the aluminum is my oxidation, and so that's going to have to flip. Let's solve for the standard E cell before we start to adjust anything. So I'm going to take the cathode value minus the anode value. So that's negative 0.13 minus a negative 1.66. So I get a standard E cell of 1.53. So when Pb is reduced and Al is oxidized, we get a positive voltage on the wire. So then I'm going to balance these half reactions. And so I see that I just need to multiply by 3 and by 2 so that my electrons cancel. And so here is my balanced redox equation. All right, both of my solutions are starting at 1 molar. And so I'm going to do a little BCA table. I know that I'm going to use up some of this Pb2 plus, right? Because as the electrons come on the wire, the Pb comes over and takes those electrons. And so the ions are being used up minus 3x, whereas the aluminum is being produced because the solid aluminum from this electrode loses the electrons that travel on the wire, and it then dissolves into Al3 plus. So we're going to have a positive 2x here. So I need to solve for x, but let's use this other hint. Aluminum 3 plus changed by 0.6 molar. So what that tells me, because I know I'm making more of these Al3 plus, that my final value has to be 1.6 molar. I started at 1 and it changed by 0.6. How do I know if I add or subtract? Well, because the aluminum 3 plus is a product, it's being made, we're going to end with 1.6. So we're going to use this column right here to solve for x. Okay, 1 plus 2x has to give my afterline. So 1 plus 2x equals 1.6. I solve for x and I get 0.3 molar. So now I can solve for the final concentration of Pb2 plus. 1 minus 3 times x gives me what my Pb2 plus is at the end. So 1 minus 3 times 0.3 gives me a leftover of 0.1 molar. So now we're going to use the Nernst equation. Q is my products divided by my reactants. I'm not worried about sneaky solids, so Al and Pb, we don't care about sneaky solids, so it's going to be Al3 plus squared over Pb2 plus to the third, okay? So we found our standard E cell 1.53 minus 0.0591 over the 6 moles of electrons that we canceled out up here. And then we're going to take the log of my Q, and my Q is what we get at the afterline. So Al3 plus is 1.6, and that's squared because of my Q expression, divided by, we found that the question mark was 0.1, so 0.1 cubed. So my new E cell is going to be 1.53 minus the result of all of this, which was 0.034, and so my new E cell value is 1.50 volts. I'm just killing it today helping you with these problem sets. Here's objective 3, number 59. You will still need to do letter B. So I'm going to do A and C. You will have to do letter B. But you're going to use the standard reduction chart in the back of your book to tell me if H plus is capable of oxidizing copper solid to copper 2 plus, and if H2 gas is capable of reducing Ag plus. Why don't you give these a try, or at the very least find these half reactions that we need on your chart. All right, so for letter A, is H plus capable of oxidizing Cu solid to Cu2 plus? So here's my half reaction written as a reduction. Here's my half reaction written as a reduction. I found my reduction potentials. So that means because the copper reaction is 0.34, this is my reduction, okay? And so that means this top reaction will be the oxidation. So H plus will be oxidized, right? It cannot do the oxidizing. Capable of oxidizing means that this thing will be reduced and this will be oxidized. And what we're seeing here is that the copper is actually going to be reduced. So this is not true, or you could prove it by calculating the E cell, right? If we calculated the E cell of what they're asking for, it would be a negative value, which would not happen, right? We'd have to take 0 minus 0.34 if we solve for what they're asking. So we know this would actually be reduced, but they're actually asking for it to be oxidized. Let's check the next one. Is H2 capable of reducing Ag+? So I have that same half reaction. I have the Ag+, and so I can see that my Ag will be, this guy here will be reduced, and so the oxidation is happening here, which means, yes, H2 is capable because that is my oxidation. Why are they saying H2 instead of H+? Remember, we flip the oxidation, so H2 would be a reactant. Okay, solve for the E cell that they're asking for, right? We're going to take 0.8 minus 0, reduction minus oxidation, which is what they're asking for. Reduction is the Ag, H2 is the oxidation, so we get a positive voltage. All right, the last thing that we need to talk about for this section are called concentration cells, and it is possible to create a voltage on a wire if the half cells are made of the same quote-unquote stuff. We can get a current. The only requirement is the stuff has to have different molarities. So we can use the Nernst equation, and instead of products divided by reactants, because technically they're the same half reactions, we're going to do the anode over the cathode, and the electrons flow from the anode to the cathode, which is going to be the low concentration cell to the high. So we're really taking the low concentration cell divided by the high concentration. So we, again, can make the cells of the same chemicals, but the electron, and we can get some electrons to flow on the wire if the two half cells have different molarities. If they are both 1 molar or both 0.5 molar, no electrons will flow on the wire. But if we have one that's 0.5 molar and one that's 1 molar, the electrons will flow from the low concentration to the high concentration. All right, so this one is similar to your objective number 68. It's number 67, so this should help you out with it. But it says, consider the concentration cells shown below. Find the cell potential for each of these when the Ag plus in the compartment on the right is the following. So we have for both of them Ag solid and Ag plus aqueous. So our half reaction is Ag plus an electron makes solid Ag. Solid. And so my first thing, if we have 1 molar and 1 molar, when we take our E cell, because they're both 1 molar, right, our anode minus our cathode is going to be 0.8 minus 0.8 because the reduction value, I'll say reduction, is 0.80 volts. So 0.8 minus 0.8, that's not going to give me anything, right? The other two, let's solve using the Nernst equation. Remember, Q is going to be your anode divided by your cathode. Your N is your moles of electrons, which is just going to be 1 mole of electron transferred. And your anode is the low concentration flowing to the high concentration. So let's have you try B and C. Pause the video. I'll put the answer up in 3, 2, 1. All right, so like I said for this first one, they're both 1 molar, so E cell is going to be 0.8 minus 0.8, which gives us no voltage. If you have the same molarity and the same stuff, nothing's going to happen. Okay, now let's do the next one. So I have 1 molar and 2 molar. Low concentration is going to be the anode, so the electrons are moving towards the right on the wire. Okay, we take the standard cell for my Nernst equation, which was 0, right? When they were both 1 molar, which is standard, our voltage was 0. We're going to minus 0.0591 over 1 mole of electrons because there's 1 mole transferred times the log of the anode, the low, over the high, 1 over 2. And I get a voltage of 0.018 volts. So again, these standard cells don't have a huge flow of electrons, not a big voltage on the wire, but there still is some electrons being transferred. Let's try the next one. we have 0.1 molar for this cell on the right. So that means the anode must be on the right now, because the anode is always the low concentration. Electrons flow from the anode to the cathode. So still 1 mole of electrons. Our standard voltage is still 0. We're going to take Q, the anode, over the cathode, so 0.1 over 1, and we get a voltage of the wire moving from right to left of 0.0591 volts. So there's how you calculate your voltage for a concentration cell. Hey guys, if you need a stronger foundation on how these cells work, here's a great video to circle back to. And there's some times on there as well. We watched this in class, but the link is available. If you go to the electrochem module, there's a little page towards the top that gives you extra videos that might be helpful to watch. So feel free to circle back to any of those if you need some reinforcement. Talk to you in class.